So the tangent plane has in it, in a way, fx and fy. They combine to create that tangent plane. They're sort of the vectors that lie in that plane in a sense. Are you guys semi getting the idea? It's not exactly what I'm trying to say, but they go into creating that tangent plane.
So all the vectors are on it or in it?
Well, those two mean about the same thing. Let me give us some pictures to look at real quick here. All right, here we go. Where are you? Where are you? There we go. All right, let me just bring back up. Okay, it's not what I want. So here is the tangent plane. I hate this picture, but it's the only one here. Too bad. So that plane, the direction of that plane, the x direction of it is determined by, well, fx, right? I mean, that's where it orients itself is dependent on what the value of fx is. And the value of fy determines, sort of determines where it's pointing in that direction. So as I move this tangent plane around, and I think there was an animation, oh, that's the one I had to find elsewhere. Let me see here. I'm going to find it. All right, anyway. So I had found something somewhere else. It wasn't in the book, but they had a really nice application where you could just move the point along, and it kind of follows the tangent plane along. Yes?
So essentially the fx, fy tells how much the plane tilts or where it's tilting to?
Yes, in a sense. I like it. All right. So what's funny to me, and I can't believe this is a beautiful place to have some really nice pictures of what's going on. So there's a lot of work to go through. What we're trying to construct now, what I've been promising for a while, is these things called directional derivatives. So not just fx or fy, but actually what's the derivative, how much is the height changing in any arbitrary direction that I want to go in, right? So that's where we want to try to get to. But what I can realize is I've kind of got fx in the I direction and fy in the j direction. And this is all in the xy plane, like my input plane. If I say that, is that understood? Right? I keep trying to really make that point, hammer it home, that the entire xy plane is where my inputs live, and above it lives the outputs. So if I want, I think there's a decent picture in the book. We can go through this kind of work. Let me just show you the work I'm trying to save us from that you can follow in the book if you want to. We can go through this kind of work here. So let me build this up. So given some function f, and we want to know the derivative of f of x, y, and some point x naught, y naught. And we want to know the derivative of the function at that point in the direction of some unit vector. Now, why would that vector that I want to talk about, why would I need to make it a unit vector before proceeding? If it had its own length that might do what? Like the slope's supposed to be 2, and I have a vector that has its own length. That length might interfere with that and make it twice as long, or whatever it's supposed to be. So, given a function and a point x naught, y naught, I want to know the derivative in the direction of some arbitrary unit vector. So we'll call it u to make it hammer it home that is a unit vector. So they ask me to find the directional derivative in the direction of 3, 4. The first thing I want to do is make that into a unit vector. So it doesn't interfere with the actual length of the derivative itself. All right, maybe. So what ends up happening is, let me see. So let me show you the full blown out, by the book kind of definition of this. You'll enjoy this. How do I find the derivative of a function f of x in Math 180? What's the official definition? Let's start there. That thing you guys...
Limit.
Yeah.
As h goes to 0. F of x plus h. F of x plus h minus f of x over 8.
I like it. And we sort of use that same format to start talking about partial derivatives, right? So it's all about starting at some x and going a little bit away from it. You guys kind of with me? So now watch this. This kind of makes some sense if you just look at this. So now we're saying for this kind of function, f of x, y, I could do this. The directional derivative in the direction of this unit vector of this at some point will be the limit as h goes to 0. Now here I stepped a little bit away from x. In what direction? I didn't have to specify in 2D because what direction is the only direction I can go with my inputs? Left or right, right? So I can go plus h or minus h. You know, you guys understand what I'm saying. I don't have to specify a direction in 2 dimensions because there's, for my inputs, there's really just that one dimension to move in.
Is this going to be f of x plus a, y plus b?
Almost. We want to let that step. We want to let that step away from that go to 0, right? So it's not going to be quite this, but it will become this. Where'd you go? There you go. Of course, everyone out of room. F of x naught, y naught, all over h. Now let's see how this relates. So I step a little bit away from x in the x direction. So here I do the same thing, because what's a? What's a? Here, going back to here. So the directional in the direction of u, and u is ab. So a is the x component of the direction I want to go in. So I step a little bit in that direction, and I step a little bit in the y direction of my vector. Let me let that sink in for a minute. It's the exact same thing we did in Math 180. I just have 2 variables that I have to take care of now. Right? So I could just step away from him, just h away from him. Because it's all about, because now what's kind of like the vector, what's my direction vector now, back in Math 180, my inputs are going to be in what direction? It's all going to be based on the vector what? I. So back here was 1, 0. So a would have been 1. So I would go x plus 1h. I really want you guys to realize how this definition is exactly the same as this one. I'm just now allowing myself not only to step away from the x a little bit, but also to step away from the y a little bit. All right. In fact, if you look at your number, what number was that one with the linear approximation? Number 1. 1e. Isn't that what I did for my input point? I stepped a little bit away from the endpoint for the x, a little bit away from the endpoint for y. So some of you guys that went up or down, it doesn't matter. I like it. So these are the same definitions. Do I want to apply this definition to discover directional derivative? Let me just ask you, do you want to apply that definition?
No.
All right, good. We're not going to. I like it. This is one time I won't make you do it. You could.
You could redefine all the product rule.
You could. You could totally, and it would eventually match up with what we're about to do anyway. Right? So once we've got a lot of stuff under our belt, we should be able to maybe go back there and build up what we need from the stuff we already know. We don't have to completely recreate the wheel. Yeah?
When you say X naught, Y naught, is that a point or a thing?
It's an input. So one thing I really want to make sure you guys understand is this is Z, right? So when I'm talking about this, where does this vector live?
XY plane.
In the XY plane, because I'm talking about as my inputs change, or if I face in this direction on my input plane. So when I look at fx, it's really, I have some surface up here, I'm at some point on it, which relates to this input, and I can say, well, how much does the height change if I look that way? And of course, what vector would control this direction? 1, 0 again, right? It would just be I. Or I can do Fy, and that would be 0, 1, J. But now I'm saying, what about that direction? And that would be U. Can we let that sink in for a minute? It's really going to become a lot more in your face, this looking at 2D representation of inputs and thinking about what they mean for the outputs and what the derivatives mean, just like was on this test. Yes?
I mean, and that X naught, Y naught, is it a point?
It's an input point.
So do it have, does it have like Z naught?
It would.
Just you don't say.
We don't care. It's sort of like, I could give you this question from Math 180. Find the derivative of f of x equal to 2x squared minus 7 at x equal to 3, right? That sounds very familiar, right? Hopefully. If I gave you that, you all should eat that up and spit out the answer and go to the next one. No problem. So that's what I'm doing here, except why can I just say at x equal to 3? Because you can calculate your own y if you want it, right? So it's all about at the input, what's happening to the output. At the input, what's happening to the output. Does that answers your question? Okay. So this is not a point that lives on the surface. This is a point that lives in the input plane. I like it. Just like this point lives on the x-axis, which is the input line in that case. All right, let me stop there for a minute. Let you absorb it and think, what kind of question can I have out of that? Some of you guys look pained. It's about right. Okay. All right, I like it, maybe. So we're going to be talking a lot about, we're going to have a lot of symbols that reference only x and y, just like this does. Because the output it's just, I could always get that output if I needed to because I have the function that I'm working with. So I don't care about the output when I'm talking about the direction of slope. Same thing I said, like a more in-your-face thing about limit is, what's the only thing I have to reference here if I wanted to give the correct two answers for the two possible limits? I have to do as it goes from above, so as the x values come down to here, as the x values come up to there, I'm not concerned about the y's. I can then see what the outputs were, but what my first thing is, as the x's come from above, as the x's come from below, and then I can look to see what the output was. Here, I'm talking about what are my inputs, and what is my surface doing from that point? Is it going down from that point in that direction? Okay, maybe. Okay, cool. So, here's what I was trying to say earlier. So, I have this fx idea, I have this fy idea. I should kind of see how to be able to put that together for this unit vector in the direction of the unit vector. How do I get the... What's another way? I really just want you guys to... How can I get what this derivative would be using these as building blocks now?
Cross product.
No, I don't want to step out of this plane. Cross product automatically throws me out of that plane.
Dot product.
Dot product. I love it. So we're going to come at that from two different directions. So I should expect there to be a dot product eventually. And we've actually already seen what we're going to get. We're just going to get to it a different way. Blah, blah, blah. Oh, yeah. Okay. In fact, let's just do this directly. Let me see what you guys think of this. And how do I make sure you understand that we've already done this kind of thing? Let me just write it up here. So this is where U is pretty much always going to be defined like this for us in this section. U is that arbitrary unit vector on the input plane. So this is going to end up being just this, fx at x naught y naught. This is at x naught y naught times a plus fy x naught y naught b. So it's building blocks. So I'm saying this is sort of like my new I hat in a way. This is my x direction building block that I can use. And then this is the same idea here. It's another building block. So I'm really taking that u vector and breaking it down along these things here, along those directional, and along those partial derivatives. So a total derivative in the direction of AB is going to be the x derivative times the A and the y derivative times the B. And that does come up, another way to write this would be, this is where it gets a little more interesting. How can I write this? What would be what dot what would be represented by this?
AB done.
Yeah, let's put it in the same direction. So let's see, fx, fy, dotted with AB. All right, let me let that sink in. This is 14.6, by the way. Oh, cool. Okay. So really, this is that idea. If I'm looking at my input plane, and I've got this point that I'm interested in, x naught, y naught, and I want to know, okay, what's the derivative in this direction? What is the derivative? How much is the height changing? If I'm standing here looking up and I go this way, how much will the height change as I start to go in that direction? That's the question. Well, I know how much is going to change in this direction. That's fx. And I know how much is going to change in that direction. That's fy. So together they make their own, what do you want to call it? Vector. I like it. So if I dot these together, I see what the resultant is just in that direction. How much of those lie along those lines? So if I wanted to do, for example, if I had, so I had a point, got my fx, fy, and I want to know in this direction. So let me see how I can do this. Obviously, in this direction, that's going to be
I.
exactly. So my unit vector is going to be I. If I dot fx, fy with I just get fx. And I can do the same thing if it's along the y. So really,
You mean new FX.
say again?
Like a new FX.
No. This is the fx for this function that I'm given. This function I'm given has an fx. The function I'm given has an fy at a point. And we can calculate those no problem. I really want you guys to put this together with what we were doing earlier with vectors and realize I can get any other vector direction using those two components to help me figure out what would be along that vector. And that would just be taking the dot product. See how much of these lie in that direction. That's really all it is. It's almost too nice to believe. And this piece here, this is insanely important. This is called the gradient of f. It's this vector here. I like it. And you can extend this to however many dimensions you want. And the gradient is used, sometimes it's read del f. I never say it like that. I'm just going to say grad f. Just because that's the way I was taught. So it's already stuck in my brain that way. But what this is composed of is just all the partial derivatives. So it's sort of like a building block, a collection of building blocks. So if I have a certain direction that I want to look in, and I know all this already about my function, I can just take the dot product and see what the derivative is in that specific direction. So before we were just able to do fx and fy. Okay, maybe. So let me give you an example. What if I knew that fx was 2 and fy was 7? But I want to know, okay, what is it from this point if I look at 45 degrees? What would the derivative be then? What's that directional derivative going to be? How would you figure that out?
Magnitude cosine theta. So would it be cosine theta equals?
Couldn't it just be the unit vector of like?
So what's the unit vector? What's the unit vector that 45 degrees represents? What's represented by 45 degrees? What unit vector is that? And that's just really going back to unit circle. No, it can never be 1, 1.
2 over.
Really quick, I want to make sure you guys understand. 1, 1 could never be a unit vector because the length of 1, 1 is 2, square root of 2, right? No good. So it's got to be just cosine and sine values. It's just coming right from the unit circle. That's really all it is. So that was the whole idea of cosine, the directional angles, directional cosines, that whole thing. Because they'll always end up with unit vectors that only denote direction. Okay, I like it. So this would be what now?
Root 2.
2 over 2.
Yeah, root 2 over 2. Root 2 over 2. So then I can dot that with 2, 7. Because one thing that's kind of weird here is I keep going in the same direction, so it's a little bit strange. But doesn't this have, and this is obviously not drawn to scale. Let me try it a little bit better. 2, 7. Doesn't this have this is what that actually looks like, right? That is 2, 7. Are you with me?
Is that your AB or FX at 5?
What was this? fx and fy. I like it. So they make this vector. This is what we call now, this is called the what? Gradient. I love it. So that's the gradient. The gradient has all the information about the partial derivatives from some point. I like it. It could be any dimension you want to live in, right? Or want to realize that we live in. So now if I take this, which is about the direction I want to go in, and dot it with this, which is the gradient, it won't screw with the length of this at all, because this is a unit vector. So the slope will still have the right length, it just will be pointing in the correct direction. Yes?
That's A and B, right? Right 2 over 2 and right 2.
Yes, exactly. That's AB for a 45 degree angle. 11. So they could ask you a question about if you're at a 60 degree angle, what would the directional derivative be? Okay, so then you got to realize it's cosine 60, comma sine 60. Or they could say, what is the directional derivative in the direction of 5, comma 8? Well, then the first thing you got to do, like I said earlier, the first thing you got to do is take 5, comma 8 and divide by the length to make it a unit vector. So there's two different ways you can be given a problem, but they both deal with unit vectors. That's the important thing. All right, so let's try a concrete problem out. That might help us out a little bit. So say given let's not get too freaky. Find DUF. Well, let me just say this. Find the directional derivative. Doesn't matter. Sure. All right, so there's a lot of information packed into that little sentence, right? So we have to really unpack it. And this is what a lot of you guys did to yourself on the question. I can't remember which one it was on the it was where you had to create the tangent plane. And you put the entire function for fx in your tangent plane equation. I was like, oh my God. I always find my slopes first and then put that number in there, right? So you're allowed to do that completely. And part of it is, as a student, you're not really allowed. Is that enough work to show? Does he want this whole damn thing? That looks like something he would like, all this mess. No, I don't like mess. I don't like that. I'd rather do parts of it on its own and plug those numbers in. So I need to figure out what? So I know that the directional derivative is defined to be this kind of thing. So there's two things I have to take care of immediately. And that is, what does this relate to with what I was given? I like it. So this is related to that, but why is that not equal to this? Not a unit vector. I love it. So I have to make sure that the direction I want to face in is defined by a unit vector, because I really hope everybody now is cool with the fact that if I divide a vector by any damn thing except 0, it still maintains the same direction. And then the other thing is, where does this come into play?
Those are your x out, y out,
For
right?
your fx and fy.
So to get here, and remember, I'm just lazy, so I'm not writing fx evaluated at x naught, y naught, fy. These are just going to be numbers. These are going to be derivatives, partial derivatives, of the function at this point. Just going to be numbers. So I have several things I got to work out on the side. I can figure out what fx is, what fy is, then what fx at 2, 3 is, fy at 2, 3, and then finally convert negative 2, 1 into a unit vector. So do all that. I'll stand here and look at you.
So then would you write that like du at 2, 3?
Yes, I love it. Your final answer could be denoted like that. I like it. All right, you guys, what do you get for fx?
2y squared.
Yeah, 2y squared. And what about fy?
4xy minus
Yeah,
7.
4xy minus
7.
7. I like it. And then we got, so 2, 3, the only thing I have to worry about. And look at you real quick. I want to talk about something real quick. Just to get you ready for a possible dreaded Jeff conceptual question. Fx depends only on y. What might that mean?
It doesn't matter what x you put in there, because y is the only.
Yeah, so since fx depends only on y, that means so at the point 2, 3, will fx be different than at the point what you got, Jeff? 7, 3.
No.
No, okay, so that's how you start to figure out what that might mean conceptually. All right, I like it. So there's going to be actually a lot of those kind of questions, especially related to second derivatives, right?
So it's a line.
Well, you got to think about, this means the rate of change of the height as I move in the x direction. So it doesn't matter what the x value of the point I start at. So along a vertical line in the input plane, oh shit.
It means it's gonna look like it was cut off or something.
I really want this to make sense. So why do I say a vertical line in the input plane? We don't know, Jeff. You're just talking shit now. So no matter what the x value is, does fx care?
No.
No, fx depends only on y. So it's going to have, so fx, what will be special about fx along that entire line? Not special, but it's going to have the same value along that entire line. So however the height is changing as I look this way, it's going to be changing at the same rate along any vertical line that I draw. And then you can kind of go further with it, and what would that mean about the shape of the surface type of thing, right? And Fy, of course, is a combination. Yes?
Wouldn't that be a horizontal line? It doesn't depend on that.
So here I've got, this is the point, well here's 2, 3, for example, right? Here's 2, 3. And so if I go to 7, 3, oh yeah, you're right. What do I want? Yeah, I want to be able to change x and it won't care. I'm with you. Yeah, okay. Cool. So if I was at 2, 3, it doesn't care. And if I was at 7, 3, it doesn't care. It's the same